Welcome to lecture 16. In this lecture, we're going to get started on RC circuits, which is what you get when you combine resistors and capacitors. I'm guessing this is something you haven't seen before, so hopefully this will be real interesting. Let's just do a real quick recap about capacitors and resistors before we combine them to make our RC circuits. So if you have a circuit with some potential source like a battery and a capacitor, then what happens when you connect your circuit is that charge is going to flow around the circuit until your capacitor gets fully charged. The capacitance is the charge on the plates divided by the potential of the batteries. So when your capacitor is carrying a full potential of epsilon, that's when the current stops flowing because it's fully charged at that point. If we add up capacitors in series, we know that we have to add up the reciprocals to find our equivalent capacitance. For capacitors in parallel, you get the equivalent by just straight up adding them. So that's your rules for adding series and parallel capacitors. Then with circuits with resistors, if we connect a resistor to a circuit, then a current is going to flow around the circuit. We find that current from Ohm's law. It's potential divided by resistance. You can have combination circuits. Any circuits where you have resistors in series, you can find an equivalent resistance by adding them up. And any circuit where you have resistors in parallel, you find the equivalent resistance by adding up the reciprocals. So that's a recap of what we've done so far. Maybe the main thing to take away here, the thing to remember as we're doing our circuits, is that a circuit with resistors and a battery has a steady flow of current. A circuit with a battery and a capacitor will have a changing current while the capacitor is either charging or discharging. So that's going to be the foundation for what we talk about. To get you warmed up, and we're going to circle back around to this a little later on, I'd like for you to try as an at-home project or just a little homework project, show that the units of the product of resistance and capacitance are seconds. So when you multiply an ohm and a farad, you get seconds for your result. That's going to be important, and we're going to come back to that. The next thing you can try at home, and I've got one quickly here I can play, is to use the capacitor lab on FET to look at the discharge time of a capacitor. So what I mean by that is if we get a capacitor fully charged up by attaching it to a battery, and then we attach it to something else, something that uses energy like a light bulb. How long it takes to discharge, how does that depend on the capacitance? So I've got two extremes here in this simulation. First, I'll take my capacitor, hook it up to the battery, it charges right away, then I attach it to the light bulb. Discharges pretty fast when the capacitance was 0.09 picofarads. Now I'm going to increase the capacitance by decreasing my plate separation and increasing the area. Now my capacitance is huge. I'm going to hook it up to the light bulb. You see now, when the capacitance is so long, it's taking a longer time to discharge. There's been more energy stored, so it takes a longer time to use it up. These are some things we're going to look at as we go through this chapter. So we're going to start asking what happens in circuits with resistors and capacitors, and those are called RC circuits, R for resistor, C for capacitor. The basic kind of circuits we're going to look at are going to have a potential supply, a battery labeled with epsilon, so epsilon for potential. There's going to be a switch which can open and close. There's going to be a resistor with resistance R and a capacitor with capacitance C. So, excuse me. Those are the circuit elements that we're going to see. So we already said that circuits with resistors have constant potential. Circuits with capacitors have changing. Sorry, I mixed that up. Circuits with resistors have constant current. Circuits with capacitors have changing current. Circuits with resistors and capacitors, we use those for timekeeping kind of circuits like intermittent wipers, where you want current to flow sometimes, but not all of the time. So our basic system we're going to look at, we'll start simple where we have an open switch. And we're also going to begin with circuits that have a capacitor and a resistor together, and the capacitor is fully charged. So that's where we're going to begin. Of course, we'll get a little bit more complicated as we go on. Then we're going to close the switch and we're going to describe what happens. So we're going to close the switch. So instead of being open, it's going to move down. We're going to complete our circuit. Well, we know what's going to happen is that charge is going to flow because all of the positive charges on the top plate of that capacitor are going to repel each other. They're going to push away. To get away, they're going to flow along those lines. So charge is going to flow until the capacitor is discharged. So that's what happens. What we're going to try and figure out now is what is the current in that circuit. We know current is flowing charge. We know that the charge flow is changing. So let's see if we can figure, and it must be changing because it starts when it's flowing and it stops when it's not flowing. So there's a change from moving to not moving. So let's figure out, see if we can find our current. And let's see if we can find it as a function of time. What is our current at any specific time? So let's get started. Let's look at our circuit before and after we close the switch, and let's establish our notation and the fundamental equations we're going to use to figure out what is the current as a function of time. So we'll begin with the case when the switch is open. When the switch is open, of course, current cannot flow. Our capacitor has capacitance C, and it carries a net charge that we'll call Q with a 0 on it. That stands for the charge Q at time t equals 0. There's also going to be a potential difference across the plates of the capacitor. So that'll be our initial potential difference. We're going to call that delta V 0. Just kind of as a side note, you might wish to remember that if capacitance is charge over potential, then potential is going to be charge over capacitance. So that's good to put in as well. Okay, so that tells us about the capacitor. What about the current? Well, if the switch is open, then the current through the resistor is equal to 0. So if the switch is open, there's no means by which the charge to travel. If the charges can't travel, the current is 0. If the current is 0, then the potential difference across the resistor is delta V of the resistor equals current times resistance equals 0. Okay, so that's what happens before we ever open the switch. Our next step is at t equals 0, let's close the switch. That means now we have a closed circuit and charge is allowed to flow. So what happens is that the charge is going to be drawn off that positive plate and current is going to begin to flow around the circuit. So that's what's going to happen with our current. Let's label that current I. Now let's ask what happens or what's the situation at some general time t. So at time t, what do we have going on here? The net charge on the capacitor is no longer QO because some of the charge has traveled off the capacitor. So on the capacitor plates, it has some general charge Q. It's less than QO, it's bigger than 0, somewhere in between. And the potential difference across the plates of the capacitor, delta V for the capacitor at time t, is however much the charge is divided by the capacitance. So that's what's happening across the capacitor. What's going on across the resistor? Well, across the resistor now, delta V across the two ends of the resistor. First of all, it's negative. Our capacitor is supplying potential to the circuit, and we're getting a potential drop over the ends of the resistor is equal to minus current, whatever the current is, times the resistance. So that's what's happening. In terms of drawing the pluses and the minuses, so the top plate of our capacitor is a positive. That means the top end of the resistor is positive and the bottom end of the resistor is negative. So we get a potential drop when we have the circuit, when we have the current flowing through the resistor in the orientation shown. Okay, so where can we go from there? Like we've done in previous problems, we can apply Kirchhoff's potential law, or the loop rule. So if we pick a loop that comes around our circuit, I'll pick a clockwise loop, we can write down Kirchhoff's potential law. What we have in Kirchhoff's potential law is delta V for the capacitor, so the potential increase across the capacitor, plus delta V for the resistor equals 0. Sum of all the potentials around any closed loop equals 0. Okay, next let's fill in what we know about delta V for the capacitor. Well, that's the charge on the capacitor divided by the capacitance. Let's fill in delta V for the resistor. That's minus because we have a potential drop. Current times resistance equals 0. Okay, here's our fundamental. Here's our setup. So now we've looked at the system with the switch open, then we close the switch, and we've thought about the charge and the potential at each step. Next, we'll move on to solving our equation to find an expression for the current as a function of time. Just before we start solving, let's make sure we know exactly what we're looking at and what our definitions are. Q is the charge on the capacitor at time t. And I is the current through the resistor at time t. That means Q and I are the instantaneous values of charge and current at our general time t. So it's an instantaneous value. That part is really important. So now let's remember a general definition we have of current. So our general definition of current is that current is change in charge over change in time. For this problem specifically, our current is still change in charge over change in time, but our change of charge, dq, is equal to minus d of big Q. So now this is kind of important. dq is the amount of charge that gets pushed through the resistor when our charge Q is decreased by a little amount dq. So why don't I even put that in notes there? So dq is the amount of charge through the resistor R. And that happens when the net charge on the capacitor plate Q is decreased, because it's a discharging capacitor, by a small amount of charge, which is dq. Okay, so dq is the amount of charge going through the resistor. D little q, I mean, is the amount of charge going through the resistor. That's equal to minus, because that amount of charge on the capacitor plate is decreasing, the little amount of charge that's leaving the capacitor plate, which is d of big Q. So then that gives us, for our current, I is equal to minus dq dt. So now our strategy is we're going to put this expression into this current, and we're going to solve for our charge Q. So that's where we're going from here. Let's get going now on solving our problem. So we know Q over C minus IR equals 0. That comes from our Kirchhoff's potential law. Q is the charge on the capacitor, C is the capacitance, I is the current, and R is the resistance. First thing I'm going to do is plug in what we just found for our I. So Q over C minus dQ by dt times R equals 0. So divide everything by R, Q over RC plus, so minus times minus times minus gives us a plus, dq dt equals 0. So dq by dt equals minus q over rc, or 1 over q dq equals minus 1 over rc dt. Now, just before we start to solve, we might notice here that R times C is the resistance times the capacitance. That's a constant for any given circuit. So once you design your circuit or you build your circuit, the resistance and the capacitance won't change, so R times C is a constant. We want to solve our problem now, so we're going to have to integrate both sides. Let's just move on to the next slide so this one doesn't get too crowded. To keep going with our solution now, we're going to have to integrate both sides. So the integral of 1 over q dq equals the integral of minus 1 over rc dt. This is kind of interesting because the next thing we need to do is to pick the limits of our integral. The limits we should pick for our integral would be from the beginning of the problem to the end of the problem. Now, that might sound a little bit vague, but beginning to end, it applies to both time and charge. At the beginning of the problem, the amount of charge on the capacitor plate is what we called Q0. And at the beginning, the time is what we call 0. So we start our stopwatch at the beginning. At the end, what we mean by the end is our general time t, for which we're trying to find how much charge is on our capacitor. At that point, we've got charge q, and it's time t. So now let's solve this problem. So the integral of 1 over q dq is the natural log of q. It's going to be evaluated at the limits of q and q0. The integral of minus 1 over rc dt, well, 1 over rc is a constant, that comes out front. So that means I've got minus 1 over rc times the integral of dt. The integral of dt is just t, and that's going to be evaluated at t and 0. Okay, a couple of things we can fill in here. The natural log of q evaluated at q and q0 is the natural log of q minus the natural log of q0. Then you can fill in that when you subtract two logs, you're allowed to just divide the arguments. Okay, so that's the left-hand side of our equation. On the right-hand side of our equation, we've got minus 1 over rc times t minus 0 equals minus 1 over rc times t. There's the right-hand side of our equation. Let's fill those two bits in. So I've got the natural log of q over q0 equals minus t over rc. If I'd like to simplify this, I'll raise both sides to the power of e. So e to the natural log of q over q0 is just q over q0. Then on the right, I've got e to the minus t over rc. So here's our basic expression. On the next slide, we'll just tidy it up a little bit. In our expression here, we notice that RC, which we said was a constant for any circuit, that pops up and we give that a new name. So we define tau, so the Greek letter tau, we define that as the time constant. So tau is equal to R times C. This goes back to that question I posed a little bit earlier, which was to say, show that the units of R times C work out to be seconds. This is where this comes in handy. So there's our definition. So let's rearrange our equation above. Let's solve it for Q, and instead of writing RC, we'll say tau. So Q is equal to Q0 times E to the minus T over tau. This is our expression for the amount of charge Q on the capacitor plate as a function of time. And this is for a discharging capacitor. If you wanted to work out for the charging capacitor, you would do a similar sort of working, but you might see a different expression. Okay, so that's what we've got so far. Let's just see what this looks like, and let's think a little bit more about that tau and what that means. So let's think next a little bit about what that current looks like over time. So if our charge Q on the capacitor at any time t is a constant times e to the minus t over tau, the minus tells us it's decreasing, and e to the minus t over tau tells us that it's decreasing exponentially. So Q dies off exponentially. That's kind of interesting. If we were to draw that graph, so we could plot Q as a function of time, it would follow some sort of curve, and as our time gets really, really big, that curve will get closer and closer to zero. Let's look at a couple of interesting points. What happens at t equals 0? If t is equal to 0, our charge Q is equal to QO e to the minus 0 over tau. E to the minus 0 over tau, that's 1, equals Q0. So the first point on our graph is Q0. So our charge starts at a finite number. The next one we could look at, what happens, and remember we said that tau was RC equals one time constant. What if the time t is equal to tau? What if it's equal to r times c? So then Q is equal to Q0 e to the minus tau over tau, or Q0 e to the minus 1. E is just a number you can put in your calculator. E to the minus 1 is about equal to 0.37. So at t equals tau, our charge Q is about 37% of our initial charge. So it starts to die off pretty quickly. Okay, what about at 2 tau? T equals 2 times tau. Then our charge Q is equal to QO e to the minus 2 tau over tau equals QO e to the minus 2. If you do that in your calculator, it turns out to be about 0.14 times QO. So the next point on the graph, it's gone down to about 14% of its original value. So this is kind of interesting. It gives you an idea of how fast that charge dies away. So you can do that for a few different values. When you get down to t equals 5 tau, the amount of charge left on that capacitor plate is QO e to the minus 5 tau over t. It's about equal to 0.001 times QO. It's at this time we say that the capacitor is approximately discharged. So here's something that I find really neat. If it's an exponential die-off, that Q doesn't technically go to 0 until your time gets to infinity. I think that's kind of interesting. That's not very practical though, because in practical terms, it's discharged when the charge is pretty small. And we say that happens at around 5 times the time constant. So if you're working on a problem and I ask how long does it take to discharge the capacitor, I'm asking you to figure out what is the time constant, and the amount of time it takes to discharge is 5 times that time constant. Okay, let's circle back now to the question that we asked. We asked what was the current in the circuit as a function of time. We found the charge, so our next step will be to find the current. For our last task now, let's find the expression for the current through the resistor or around the circuit as a function of time. So what is the current through the resistor? What we remember about current is that it's the change in charge over time. So I is minus dq over dt. So remember, it's the amount of charge flowing over time. The amount of charge pushed through that resistor is negative because the charge on our capacitor is decreasing. So that's where that negative sign came from that we explained a little bit before. So we've got minus d by dt of the charge, but the charge is Q0 times e to the minus t over tau. So all we have to do now is the derivative. So our Q0 is a constant that can come out front, minus Q0 d by dt e to the minus t over, well, that's kind of a funny squiggle for my tau. Hopefully you can still see it okay. When I do the derivative of e to the minus t over tau, what I get is minus 1 over tau times e to the minus t over tau. That's how those e functions work. They're a little bit funny. So let's multiply this out a bit. I've got minus q times minus 1 over tau. That gives us a plus. Tau is r times c. And I've got e to the minus t over tau. Now, this QO over RC, that jumps out at me a little bit. QO over C, that was the original charge on our capacitor. So right off the bat, we said that the amount of potential difference across the capacitor was the initial charge across it divided by the capacitance. So QO over C, that's the potential, initial potential, so that gives us V0, delta V0 over R times e to the minus t over tau. Potential over resistance, that's current. So delta V initial over R would be the initial amount of current flowing through the circuit. Since the capacitor is discharging, that would be a maximum value. So if we put it all together, the current at some time t is the initial current, I0, times e to the minus t over tau, where tau is the time constant given by R times C. So there's the current through the resistor as a function of time t. So our current starts at a maximum value and dies off, just like the charge starts at a maximum value and dies off. Something you might try to do is, could you use the equation for current and find the expression for potential? So here's a question I think I'm going to leave you to think about. So the question is, which capacitor discharges more quickly after the switch is closed? So the two capacitors have different capacitance. The one on the left is 6 microfarads, the one on the right is 5 microfarads, and they're both attached to a resistor. The one on the left is smaller at 2 ohms, the one on the right is bigger at 3 ohms. Which discharges, so which loses charge faster? So I'm going to leave you to think about that. I will post the solution with the notes. If you're looking for an excuse to spend a little bit of time on the discussion groups, you could pop over there and try and discuss with your classmates what you think the answer is and why.